So in this lecture, we are going to discuss the various types of symmetry elements. There are 5 symmetry elements are existing in the molecule. The first one, it is center of symmetry, inversion of all atoms through the center of symmetry. Second symmetry element is proper rotational axis of symmetry, CN. Third symmetry element is plane of symmetry or mirror plane, sigma. Fourth symmetry element is improper rotational axis of symmetry, SN. And last one, it is identity, and the symmetry operation, it is no change. We know that symmetry element and symmetry operations are related to each other. Without symmetry operation, we cannot show the symmetry element, or without symmetry element, symmetry operation is not possible. So the molecule possesses various kinds of the symmetry. That is, the first one, it is center of symmetry. So you can see here the center of symmetry. If a molecule can brought into equivalent configuration by changing the coordinates of every atom, where the origin of the coordinates lies at a point. Center of symmetry, it is a point at which the molecule can be brought into equivalent configuration by changing the coordinates of every atom. We can change the coordinate of every atom, then the same atom is lies at a point within the molecule into opposite axis. Then the point at which the origin lies is said to be a center of symmetry or center of inversion. You can see now the example, it is trans dichloroethylene molecule. So it is shown in the diagram. At this center, if you move this side diagonally, the chlorine atom is there, and opposite side the chlorine atom is there. It means that this molecule is having the center of the symmetry. Similarly, on this side, the hydrogen atom is lies there. Then on this side, the hydrogen atom is lies there. So it means that the trans dichloroethylene molecule has a center of symmetry or center of inversion. But the another molecule you can see here, that is a cis dichloroethylene molecule. It is not having any center of symmetry. Okay, if you move on this side, it is a hydrogen atom. If you move on this opposite side, there is a chlorine atom. So there is a no center of symmetry. Take another example of the center of symmetry. Okay, platinum tetrachloride. Okay. So this ion is having the center of symmetry. Okay, opposite side, if you move along this axis, along this opposite axis, the same chlorine atoms are lies diagonally. It means that this ion, platinum tetrachloride ion, has also the center of symmetry. Okay, this benzene molecule, it is having the center of symmetry. Sulfur hexachloride molecule, it is having the center of symmetry. Okay, so the molecule is having the center of symmetry when we are moving on to the opposite side diagonally. If the same atom is lies, then the molecule possesses center of symmetry or inversion center. So this is the first symmetry element. You can see in this diagram also. It is a very good uh, diagram to show here the center of symmetry. Okay, so this is the center of symmetry. The same atoms are lies onto the opposite side here. Then let us go to discuss the second type of the symmetry element, that is a proper rotational axis. We know that the molecule has various types of the symmetry elements. 5 symmetry elements are existing there. Now this is the second symmetry element, proper rotational axis. It is denoted by Cn. C stands for cycle and N stands for order of axis. Okay, so if an imaginary axis can be constructed in a molecule, around which the molecule can be rotated, or if we draw a line through that molecule and along that line the molecule can be rotated to give an indistinguishable configuration, then the molecule is said to possess a rotational axis or proper rotational axis. So proper rotational axis or axis of symmetry, it is a line, and along which that line we have to rotate the molecule, and if we get an indistinguishable configuration or equivalent orientation of that molecule, then we can say that the molecule is said to possess a rotational axis or proper rotational axis. Now if a molecule is rotated by an angle theta, theta it is equal to twice pi upon n, okay, then n it is a axis of symmetry, n-fold axis of symmetry, okay, and operation of rotation is given by the symbol Cn. So let us take the example to explain this. You can see the example of the water molecule is here. So when we are drawing this line, okay, and when we are rotating that molecule along this axis, what happens? We are getting the equivalent configuration. So the hydrogen atom A goes onto this side and hydrogen atom B comes onto this side. It means that the water molecule is having the proper rotational axis. So what is the angle of rotation here? It is 180 degree. And so if we put that formula into this, theta it is equal to twice pi upon n. So pi it is 180, 2 multiplied by 180 divided by 180. So n it is equal to 2. So order of axis it is 2. It means that when we are rotating the water molecule for 2 times, then we get the equivalent, we get the identical configuration. So in these 3 structures, the first and third one is same, okay. So order of axis it is C2. So it means water molecule is having the two-fold axis of the symmetry. Water molecule is having the two-fold axis of the symmetry. So axis of symmetry is a line that divides an object into 2 equal parts, thereby creating a mirror-like reflection of either side of the object. So around that axis, if we rotate that molecule, then we should get the equivalent orientation of that molecule. Equivalent means not identical. Indistinguishable orientation of that molecule, then that molecule is having the proper rotational axis. So let us take the another example to explain this proper rotational axis. Proper rotational axis. So I would like to take another example here. NH3 molecule. NH3 molecule. So let us see. Let us represent the NH3 molecule here. Okay. NH3. See. Nitrogen carry lone pair of the electrons. 3 hydrogen atoms are there which are bonded covalently to the nitrogen atom. So NH3 molecule can be represented in this way. See here. Okay. And this lone pair of the electron can be represented as like of this. And angle between the nitrogen, hydrogen, it is around here supposed to be 120 degree. Okay. Now when we are passing the axis here, when we are passing the axis through the central nitrogen atom, then, and if we are rotating this, suppose that this is hydrogen 1, this is hydrogen 2, and this is hydrogen 3. Okay. The angle of rotation, if you see the angle here, it is 120 degree. Okay, this angle it is 120 degree. Everywhere it is 120 degree. So if we rotate this It means theta it is equal to 120 degree. So this is the configuration first, original configuration. Then rotating this around 120 degree, what happens here? We are getting the equivalent configuration. So suppose now this hydrogen 1 will be here, hydrogen 3 now here, and hydrogen 2 will be here. Okay. By rotating this. This is the first operation, symmetric operation carried out along the axis 120 degree. Similarly now, rotating this around the 120 degree, we are getting the another equivalent configuration. And that configuration, it will be like this. So second time we are rotating this now. So what happens here? Hydrogen 2 will be goes to here. So this is hydrogen 2, this is hydrogen 1, and this is hydrogen 3. Again we can perform the third time rotation here. Third time rotation, passing that axis through the nitrogen atom. So this is second configuration, this is third configuration, and once again we can rotate this through 120 degree. Then we will get the identical configuration of the original one. Okay. So now hydrogen 1 will be here due to the rotation, hydrogen 2, hydrogen 3. They can be labeled as like of this. Actually all the three hydrogen atoms are same, but we have to label them. So this is the configuration fourth, which is identical here. It means that this is the first symmetric operation, this is the second symmetric operation, this is the third symmetric operation. So theta is equal to 120 degree here. So by rotating the ammonia molecule 3 times, then we are getting the identical configuration or same configuration. So we can say this is C31. This is means first time rotation. Why it is C3? See now, theta is equal to twice pi upon n, that is 360 divided by n here. Okay, so n equal to 360 upon theta. So theta it is 120 degree here, so it is equal to 3. So order of axis it is C3. It means that the ammonia molecule has proper rotational axis C3. Ammonia molecule has proper rotational axis C3. So this is C31, this is C32, this is C33, and we know the rule Cn raised to n, it is equal to identity. So in this case it is C3 raised to 3, it is equal to identity here. The same configuration we are getting here, identical configuration. So thus ammonia molecule is having the proper rotational axis, and that is the principal axis, highest order of rotation. The principal axis is that axis. Okay, the molecules can have more than one axis of rotation. Some molecule are having the more than one axis of rotation, and we can show the several symmetry operations on that rotation axis. The axis with highest order is called principal axis. The axis which highest order, that is n, it is highest, is called as a principal axis, and that axis should be taken along the z axis, and the other axes are called as subsidiary axis. So this is the first second symmetry element. Now let us see the third symmetry element. In this diagram you can see this is the example of the water molecule. So if we rotate the water molecule around this axis, this is the line which shows the axis of symmetry, and rotating through 180 degree, this atom will be here, this atom will be here. So water molecule, we know that it is having 180 degrees, so it is having C2 axis, that is shown here. only one rotational axis the water molecule is having. Then second type of the symmetry element, third type of the symmetry element I would like to discuss here, that is plane of symmetry, plane of symmetry or mirror plane. So the symmetry element mirror plane can be obtained by reflection operation. The action of reflecting one half of the molecule through a plane in order to obtain its mirror image is termed as a reflection operation. So if in a molecule there exists a plane which bisects the molecule into two parts, when we are passing the plane through that molecule is divided into the two parts, where one part is the mirror image of the other part. Just if we put our hand in front of the mirror, then right hand is the mirror image of the left hand, or left hand is the mirror image of the right hand. Okay, so similarly the molecule is having such type of the plane of the symmetry. So let us show this by the example here. Water molecule, it is having the plane of the symmetry. Now there are three types of the plane of the symmetry. Vertical plane, okay, it is denoted by sigma v. Plane of the symmetry, it is denoted by the sigma, and vertical plane, it is denoted by sigma v. So what is sigma v? A reflection which contains the principal axis. That plane, it is passing through the principal axis. It means that that plane, vertical plane, should contain the principal axis. For example, water molecule is having two vertical planes of the symmetry. This is one vertical plane. By passing the plane through this hydrogen atom A is the mirror image of the hydrogen atom B. Okay. So water molecule is having the two vertical plane of the symmetry. This is another where all the three atoms are lies there. Okay. So this is the point of intersection of the two vertical planes. This is the C2 axis which is present into the water molecule. One vertical plane, it is denoted by sigma v. Another vertical plane, it is denoted by sigma v dash or sigma dash v. So water molecule is having two vertical planes of the symmetry. Now second, horizontal plane of the symmetry. What is the horizontal plane? When the plane is perpendicular to the principal axis. When the plane is perpendicular to the principal axis, it is called as a horizontal plane of the symmetry. For example, boron trichloride molecule. Let us show this vertical plane of the symmetry. Horizontal plane of the symmetry. Horizontal plane of the symmetry. So you can see here the horizontal plane of the symmetry in this molecule. The horizontal plane is seen here. Okay, this is the horizontal plane. You can see here. That plane, it is passing through the molecule and which is perpendicular to this principal axis. In this, the principal axis is C6. It means theta equal to 60 degree. So if the plane of the symmetry is perpendicular to the principal axis, it is called horizontal and denoted by sigma h. Example, it is benzene. In boron trichloride molecule also, there is a horizontal plane of the symmetry. Okay, so benzene is a very good example to show the horizontal plane of the symmetry. So horizontal plane, it is a plane where it is perpendicular to the principal axis. Vertical plane, it is a plane where it contains the principal axis. Now let us see the another plane, that is the dihedral plane, sigma d. Dihedral plane, sigma d, a plane which bisects the angle formed between the two similar consecutive C2 axes. That plane bisects the angle formed between the two similar consecutive C2 axis is called dihedral plane. It means that that molecule is having the two C2 axes which are perpendicular to each other. Okay, and in between that two C2 axes, the plane is passing, and that molecule is divided into the two parts, where one part is the mirror image of the other part. A plane which bisects the angle formed between the two similar Conjugative C2 axis is called as a dihedral plane. Okay, so it is also defined as a vertical plane which bisects the two perpendicular C2 axes. Example, it is alene molecule. You can see here this alene molecule. Okay, C3H4 alene. This is the one C2 axis. This is the another C2 axis. Okay, this one, another C2 axis, and these two C2 axes are perpendicular to each other, and we can passing the plane through this is sigma d, and it bisects. When you are passing the plane, what happens? This hydrogen will be here and this hydrogen will be here. Mirror image. Similarly here. So the alene molecule is having the dihedral plane. That is called as a dihedral plane. So I would like to show here some diagrams. So this is the vertical plane. See another view here, vertical plane. The water molecule is having the two vertical planes. Okay. The water molecule, it is having the two vertical plane which contain the principal axis. Okay. So this is the more perfect representation to show the vertical plane in the water molecule. So one vertical plane, this is passing through the C3 axis. So this is the, sorry, C2 axis. This is the C2 axis. Okay. In the water molecule. And another vertical plane, you can see here, that is a molecular plane where all the three atoms are lies in that molecular plane. And these two planes are supposed to be perpendicular to each other. So if the plane contains the principal axis, it is called vertical plane, denoted by sigma v. So water molecule, it is having the two vertical planes. Suppose it is sigma v and it is sigma v dash. Okay. So this is the another vertical plane here, where all the water molecules are lies there, and this is the one vertical plane here passing through this central atom. This is the mirror image of this. Okay. So in this way we can show the vertical plane of the symmetry. See now this dihedral plane sigma d bisects the C2 axis perpendicular to the principal axis. So you can see this is the principal axis here. Principal axis I would like to show here. So this is the principal axis. Try to understand. Okay. Principal axis, and the two C2 axes are there. Okay. So this is the one C2 axis. This is the another C2 axis which are perpendicular to each other. Okay. This is C2 axis. Okay. And in between that there is a dihedral plane. Suppose that this is a dihedral plane. The angle between the two C2 axis and that plane, it is bisects. That plane, it is bisects. So that is a dihedral plane sigma d. So this is about the dihedral plane. It is present in the limited number of the molecules. Okay. Now let us going to discuss the fourth symmetry element, that is improper rotational axis of symmetry. Improper, not proper. Proper rotational axis, it has been already discussed by us. Now improper rotational axis. If a molecule is rotated around an axis, when we are rotating that molecule around an axis and the resulting orientation is reflected, it means we have to pass the plane. Resulting orientation is reflected in a plane perpendicular to the axis. That plane should be perpendicular to the rotational axis. To attain an equivalent orientation, the molecule is said to possess improper rotational axis. It is also called as rotation reflection axis. It means that in such a molecule, first of all, we have to rotate the molecule around that axis, and the resulting orientation is reflected in a plane perpendicular to this axis. To attain the equivalent orientation, the molecule is said to possess the improper rotational axis. It is also called rotation reflection axis. Rotation reflection axis. So there are two types of the processes. First of all, rotation of the molecule about an axis. To show improper rotational axis, first of all, we have to rotate the molecule about an axis. Then reflection through a mirror plane, which is perpendicular to the rotation axis. Then we have to reflect that molecule. We have to passing the plane to that molecule, which is perpendicular to the rotation axis. Okay, so let us show this by taking the example. Now the axis around which the rotation is performed is designated as Sn. Is designated as Sn. So let us show this. Okay, Sn. Okay, and is called rotation reflection axis. Is called as rotation reflection axis. So let us take the example of this. This is trans dichloroethylene molecule. Trans dichloroethylene molecule. Okay, this is trans dichloroethylene molecule. This molecule is having the center of symmetry. This molecule is having the proper rotational axis also, and it is having the improper rotational axis also. Now rotating this through 180 degree. Okay, see now here, rotating this through 180 degree C2 axis. So this is the C2 axis. Okay, this is the C2 axis. What happens? Suppose that this is chlorine 1, this is chlorine 2, this is hydrogen 1, this is hydrogen 2. Okay, so rotating this through the principal axis, what happens? We are getting this equivalent orientation. Okay, we are getting this equivalent orientation. Now what happens here? This chlorine 1 will be here, hydrogen 1 will be here. Now this is the chlorine 2, this is the hydrogen 2. Okay, so you can see here, this is the second orientation, this is first one, this is second one. So rotating the molecule around the 180 degree, rotating the molecule around the 180 degree. Now when we are passing the mirror plane through this, in front of the mirror, reflection, what happens there? This is now Cl2 here, this is hydrogen 2. Okay, by passing the mirror plane in front of it. Now this is Cl1, goes to back side, and this is hydrogen 1. Okay, this is hydrogen 1. So now you can see the configuration, this 1 and 3 are the equivalent orientation, is the equivalent orientation, is the equivalent orientation. So it means that this molecule is having the improper rotational axis. So to show the improper rotational axis, first of all, we have to rotate the molecule around that axis. Okay, and later on we have to pass the symmetry there, plane of symmetry. Then whatever the symmetric operation obtained due to that, that becomes equivalent orientation of the original one. So you can see here, this is the first, this is the third. Okay, see here, chlorine 1, chlorine 1 will be goes to here. Okay, chlorine 1 will be goes to here, and chlorine 2 now here. So it means that this molecule is having the improper rotational axis. Theta, this theta is equal to C2, theta equal to 180 degree, means it is having the C2, and passing the plane sigma V. Okay, so it means that this molecule is having the improper rotational axis, that is S2. Okay, this molecule is having the improper rotational axis, that is S2. Once again, I would like to explain this. You can see here trans dichloroethylene molecule, when you are rotating through 180 degree, we are not getting the equivalent configuration. By rotating that molecule around that axis, we are not getting the equivalent configuration here. You can see hydrogen one will be here, chlorine one will be goes to here. It is not an equivalent configuration of this. Okay, both are different. You can see here. First and second are different. First and second are different here. So we can obtain the equivalent orientation when this second orientation will be reflected. Then we are getting the equivalent orientation of first. In place of chlorine 1, now here chlorine 2 here. Okay. In place of hydrogen 2 here, hydrogen 1, hydrogen 2 is here. So this is the equivalent orientation. It means that trans dichloroethylene molecule is having the improper rotational axis. Okay. म्हणजे तो मॉलिक्यूल आपण आधी एकदा रोटेट करायचा. रोटेट केल्यानंतर आपल्याला त्या मॉलिक्यूलचं इक्विव्हॅलंट कॉन्फिगरेशन मिळत नाही. वी आर नॉट गेटिंग द इक्विव्हॅलंट कॉन्फिगरेशन ऑफ दॅट मॉलिक्यूल. ओके. मग जेव्हा आपण त्यामधून प्लेन ऑफ सिमेट्री पास करू, when we are passing the plane of the symmetry, then we are getting the equivalent configuration of the original one. Then we can say that the molecule is having the improper rotational axis. So here it is C2, sigma V is there, so it is S2. Okay, so it means that C2 then plus sigma V, it is equal to S2. Okay, so this molecule is having the improper rotation axis, or it is also called as rotation reflection axis or alternating axis, improper rotational axis. Now the last symmetry element, it is identity. It becomes very simple. The symmetry element identity is obtained by an operation called the identity operation. Identity operation results in the production of an orientation which is identical to the original orientation. Identity means we are getting the same orientation. That symmetry element, it is called as identity. After doing this operation, molecule remains as such and no change is made in the original molecule. There should be no any change in the original molecule. When we are performing that operation, we are getting the original operation, original molecule. It means that this is a doing nothing operation. This is a doing nothing operation. Okay. So you can see here, there are 2 points are given. First, we do not do anything on the molecule. Okay. And we rotate the molecule through 360 degree. 360 degree. Let us show this by by taking the example of a water molecule here. I would like to show this. Okay, 1 minute. I would like to show this by taking the water molecule here. Identity operation. We represent the water molecule in this way. Water molecule we can represent as like of this. This is hydrogen. This is hydrogen. Hydrogen 1, hydrogen 2. It is having the principal axis C2. Okay. It is having the C2, proper rotational axis water molecule is having. Now when we are rotating the water molecule, theta equal to 360 degree, 2 times rotation, then we are getting the same configuration of this, same configuration, same to same. Hydrogen 1 will be here and hydrogen 2 will be here. Okay, so same configuration we are getting this. So first and second are both are same. This is called as identity. It is called as identity. Okay. So generally that molecule should be rotated through 360 degree. Then we are getting the same configuration here. Okay. Then that is called as identity. So identity of operation results in the production of the orientation which is identical to the original orientation. So it becomes very simple. It is always present in all the molecules. This type of the symmetry element is present in all the molecules. अशा प्रकारचा सिमेट्री एलिमेंट हा सगळ्या मॉलिक्यूल मध्ये असतो. ओके. सो इन दिस वे वी लर्न द 5 टाइप ऑफ द सिमेट्री एलिमेंट्स. 5 प्रकारचे सिमेट्री एलिमेंट्स आपण या ठिकाणी शिकलो आहोत. Okay, 5 symmetry elements we learn here, and on the basis of that symmetry element we can study the next topic, and that next topic it is the concept of point group. So to study the concept of point group, these 5 symmetry elements are very very important. We should have to know about the 5 symmetry elements. So let us take the one example here to understand the 5 symmetry elements, if they are present or not present in that molecule. So I would like to take one example. Okay, 3 minutes are remaining. So you can just see the example here. That is a boron trichloride molecule. Boron trichloride molecule. Okay. This is boron trichloride molecule. Give the labeling to this 1, 2, 3. And let us find out here how many types of the symmetry elements are present in this molecule. Okay, how many types of the symmetry elements are present in this molecule. So first it is center of symmetry. Center of symmetry. Does this molecule it is having the center of symmetry? No, there is no center of symmetry. Okay, so this is not having any center of symmetry. Second, axis of symmetry or proper rotational axis. So what is about the axis of symmetry here? So the principal axis is here. By passing the axis through this 120-degree rotation, the principal axis it is C3 here. Theta it is equal to 120 degree. So it is one C3 axis, that is the principal axis, and it is having 3 C2 axis. This is one. This is C2 axis. Okay. This is C2 axis here, another, and this is C2 axis here. So it means that it is having 3 C2 axis. This is one C2, second C2, and third C2. So it is having 3 C2. It means that it is having the principal axis. This is principal axis. It is the principal axis, and it is the subsidiary axis. Subsidiary axis here. Okay, so try to understand about this. It means that in boron trichloride molecule there are 3 types of the 2 types of the axis of symmetry. One, it is a threefold axis of the symmetry, and other it is a twofold axis of the symmetry. Along with it is having the vertical plane of the symmetry, horizontal plane of the symmetry. Okay, vertical plane of the symmetry, horizontal plane of the symmetry, sigma v, then horizontal plane of the symmetry, sigma h. Okay, so in this way, by taking the example, we have to show different types of the symmetry elements. So in boron trichloride molecules, there is no center of symmetry, but it is having the axis of symmetry. First one, it is having the vertical plane of the symmetry. Second one, it is having the identity operation. So 3 symmetry elements we can show here in the boron trichloride molecule. Identity is possessed. Identity is present in all the molecules generally. That is E. So it means that this molecule is having now 1 minute symmetry element, axis of symmetry, then plane of symmetry, and identity. 3 symmetry elements are present into this molecule. So in the concept of the point group, we have to be noted this point. Okay, so try to understand about this. So I would like to stop here now. Okay, now you don't have to join the lecture. For the next topic, I would like to prepare the video today. That is very very important one. You have to watch the video belongs to this, how to find out the point groups. Okay, so